Yep, please remember to sign in.
What did you say?
Please remember to sign in. We will get started here in a moment. Okay. So we've been talking about reflection and refraction. And recently we discovered or talked about why exactly refraction happens. So what is it that causes light to bend when it goes through the barrier between two mediums? So we have air, water.
Sorry, I'm a little late.
So what causes light to bend as it goes through this?
Reflection?
No, it's not. Refraction is where it bends, but what causes it to bend? So why does it not go straight through? What did we talk about last time that actually makes it do this? It's a quality of waves. So when we have light coming in, what is it that causes it to not come out at the same angle that it went in? For what reason does it turn?
A change to speed.
Exactly, very good. The speed, the velocity of the wave over here on this side is different than when it's over here. So when it comes in, the first part of the wave that gets in there is going slower than the part that's still up here. So it turns and then continues on. So it's this difference in speed that actually causes this refraction. So if two mediums had the same speed, then there wouldn't really be any refraction. It only happens when there's a difference in speed. So let's look at that governing equation real quick. So we come up with this this idea that kind of encapsulates this speed difference into a single number. We call this number N is the index of refraction. Okay, and it basically tells us how the light is going to bend for a particular material. So these values are entirely what we would call empirical, where like there's no governing equation that tells you, what it is. You basically just measure it, and that's what it is for that material. So for glass, for water, whatever it is, and it's defined like this. And we'll call it. So what is C?
Say it again.
What is C?
Constant?
The speed of light.
A constant. And
Speed of light.
there you go. It's the speed of light in a vacuum. And V is the speed of light in that specific material. Okay, so this is the basic idea, is that every material has some index of refraction. And it's the ratio of the speed of light outside, like, in space pretty much. Air is pretty close to space, so usually it gets kind of, they just kind of say that it's equal. But it's the speed of light in a vacuum, and then the speed of light in some material. So let's look at some of these. So this is just a quick little list of a few of these indices of refraction. Diamond has 2.4, fluorite 1.4, glass 1.5. So all of these things have different indices of refraction. And this is what causes light to bounce off of them in very different ways. So let's look at what happens, or what this governing equation kind of means. So inside a material, light has occasionally a different speed. So what actually causes it to have that different speed? So let's look at the speed of light. And because it's a wave, what wave characteristics tell you the velocity of, or the speed of that wave? So we found that the speed of a wave was determined by these two characteristics of a wave. What were they? What are two characteristics of a wave? Or two properties of a wave? Any two, come on.
Peak, crest,
Their frequency.
the trough.
So frequency is one.
And
Out amplitude.
Lambda.
And lambda, wavelength. So the speed of a wave is frequency times wavelength. So as light goes into a material, so we'll say that this is air, and this is, we'll say diamond because it had a really large one. So the speed changes. What did we say the index of refraction for diamond was? Does anybody remember?
Was it the one you just did? The COVI?
Well, it was, that's the equation we're going to use to compare it, but it was 2.5. So you are correct that we defined N to be C over the velocity in that medium. So if N equals 1 in air, then what is the velocity of, what is this, the velocity of light in air?
1.5, 1.
What? So if N equals 1,
0.
VI equals what?
One.
Is it your question or is it 1?
No.
0. Sorry.
It's a very easy, simple question. But if n equals 1, then what does the number on bottom have to be?
1.
1, right?
Or either that or both numbers on the top and the bottom have to be the same.
Which means the one on the bottom is
2.5.
I'm not trying to play
Is
the
it that
game.
number you wrote over
solve
there?
that for x. Solve this equation for x.
X will equal C times 1, right?
Okay, and c times 1 is
C.
c. So the speed of light in air is approximately c, because its index of refraction is approximately 1. So if n equals 2.5, then what is
The same thing? So confusing.
so
1 over
2.5 equals c over something times c.
1.5.
What?
1.5.
No.
What was the question one more time, Dr. J?
So it'll be 2.5 times C. Negative 2.5.
What has to go in this box?
Say it again.
Solve this equation for what goes in this little box.
Negative 2.5.
So the first thing you notice is,
The C's cancel.
so
Therefore, you have to move 2. Well,
2.5 equals 1 over what?
0.
1 over 0 is undefined.
One.
Come on, y'all can do it.
C, right?
What?
C, right? Whatever C is, right?
No. The C canceled. So it's about 0.4 C.
Oh,
Meaning, over here, the wave is traveling at the speed of light. And over here, it's traveling about 40% the speed of light. So it's traveling much slower. So from this, we can see that a larger n value means that the wave will be traveling slower in that medium. So that's one important takeaway, is if n is small, or I'm sorry, if n is big, that means that the velocity in that thing is really small. So the thing about light traveling through mediums is that the frequency will have to be the same in both materials. Okay? So let's say that this is VI. So the velocity in some material is equal to the frequency in that material is equal to or times the wavelength in that material. So my question is, what happens? If the light is going faster over here and slower over here, what does that mean about V1 compared to V2?
Balloon.
What is the velocity here compared to the velocity over there? Is it bigger, smaller, the same?
It would be bigger, right? If I'm not mistaken.
Velocity, which one is bigger than the other? The speed of light over here or the speed of light over there?
The one over there.
So which one is bigger, C or 40% of C?
C.
Well, see, yeah, that's kind of.
Yeah,
C.
40%.
anything is bigger than 40% of itself. So the velocity is higher over here. So what does that mean about the wavelength?
Okay.
So the velocity goes from high to low.
Yeah.
The frequency has to stay the same. So what does that mean about the wavelength?
It has something to do with the speed of the wave.
Yeah, it has this to do with the speed. The speed, the frequency, and the wavelength are all related by this equation. So when you go from one medium to another one, the velocity drops, or I'm sorry, yeah, the velocity goes down. So what does that mean about the wavelength?
Mhm.
So if I make V smaller, what has to happen to this side?
Smaller, quicker.
This side has to go smaller.
Right.
But if this is the same, then what does that mean happen to this?
Then it's the same too, right?
No.
Oh, well, I knew that.
20
So you said
equals 4 times
5.
5.
That's not possible. Oh,
10
not
I was
equals
gonna say,
4 times.
oh, it's not 2.5.
So
Ooh.
this is smaller. This stayed the same,
Oh, so it's half of that.
so it went down. So the wavelength in diamond drops. The wavelength is shorter. That's the only way that it can slow itself down and still have the same frequency. So when you go into diamonds, it will have a smaller wavelength.
I was drawing that in my head. I just didn't know how to say it.
So this is what's actually going on in here, is that the wavelength gets smaller as the refraction index goes up. And it's just because of the way that the speed and everything is defined. So this is one of our takeaways. This inverse relationship. And we'll get into Snell's law of refraction on Friday. Yeah, so we're about to get kicked off, I think. Otherwise, you guys have a fabulous rest of your day, and we will see you guys on Friday.